Welcome to this new session of TMLS in Finance. My name is Nadia and I work at NILAS as Senior ML Engineer. Today, I'm honored to be here and to have the opportunity to introduce two of our amazing speakers. Before starting, I would like to remind you that if you have a question, please post it in the chat. I will collect all the questions and ask them directly to our speakers after the presentation. So let's start. Our speakers are Hannes Hapke and Joe Pru. Hannes is a machine learning engineer at Digits. He focuses on ML engineering and he applies his experience in NLP to advance the understanding of finance transactions. As a Google developer expert, he has co-authored two machine learning publications, NLP in Action by Manning Publication and Building Machine Learning Pipelines by O'Reilly Media. Joe is an engineer at Digits, focusing on data engineering and infrastructure. Prior to joining Digit mission in building the world's best software for modern businesses, Joe helped design and build the experimentation infrastructure for embedded tweets at Twitter, implemented the mobile development platform at Fabric, now part of Google, and build self-service analytics and data pipeline tools at Yammer or Microsoft. Please join me in welcoming Hannes and Joe.
Everyone, very nice to meet you. Okay.
Good afternoon, good morning. Today we would like to introduce you to one of the machine learning projects we have performed here at Digits. This is one of many machine learning projects we have performed in the last couple of months. And in this particular project, we wanted to understand unstructured data and bring it into a structured format. And in order to do that, we dug a little bit through existing research, state-of-the-art research from the last couple of years. And we would like to demonstrate to you how we took the research and brought it into production and build it into our production system. Today, as Nadia mentioned, I have the great opportunity to present this topic here with Joe, and let's get started.
All right, cool. So Nadia did an excellent job introducing Hannes and myself. So I'm gonna skip these and start by introducing what is Digits and why is ML critical here. So Digits is a real-time finance platform for modern businesses. In the past, to get a pulse of your finance health data, you may have to, inquire with your accountants or log on to your legacy accounting software. But here at Digits, we really strive to deliver those insights in real time. And as you can imagine, machine learning is really critical to delivering that real-time promise. So we work on a wide range of ML problems. So like deep learning generated embeddings, various classification problems, and named entity recognition, to name a few. So we are a very small team after all. So we heavily focus on ML ops and automation so that we can pair up a domain expert like Hannes and a traditional background software engineer like myself to really test out an idea and bring a model from concept to production with ease. So today we are going to use to talk to you about how we use named entity recognition to solve our problem, to understand the useful bits, the meaningful bits out of unstructured transaction data. So Hannes is going to talk to you about how we dove into the state-of-art literature, looking for ideas, and how we prototyped them and implemented them, and a few learnings we had along the way to share with you. So you can see from this wall of text that these are just the normal transaction strings that you might see. So there's a lot here. So you can see probably a date, phone numbers, maybe a payment provider like PayPal, and a location, San Francisco in California. And in some cases, so like Uber, the ride-sharing service concatenated with a person's name. And in another case, a wire transfer. So let's zoom in into this highlighted example. So here we can see, yes, this looks like somebody used a debit card to pay a service called Cloud HQ on February 13th. And we know that the Cloud HQ is likely based in San Francisco, and here's their phone number. So as a human, this is what we like to extract from this transaction stream. We got a date, the vendor Cloud HQ, their phone number, and the location, San Francisco in California. So these are like very typical named entity recognition problems where we would like to identify the meaningful words and phrases out of this unstructured text, and then assign a label to it. So here we have date, entity, phone, and location. So how do we teach a machine to do the same?
In 2019, the Google folks published a paper around BERT, which is the bidirectional transformer for language understanding. And already in the paper in 2019, they mentioned that then this architecture can be used for named entity recognition, and they tried it out on the Canal dataset. So we saw this paper, and we were wondering, how can we apply this technology on our side here at Digits, where we exactly have the same problem? So just as a quick recap, when we talk about BERT, we're talking about a pre-trained machine learning model, which is pre-trained by Google and provided through TensorFlow Hub. And originally, BERT is trained on two tasks. It's trained on a masked language model, meaning we have a sequence of tokens, we remove some or mask some of those tokens, and then we ask a machine learning model, in this case BERT, to predict which is the correct token or which one is a missing token. And then it was also trained on a second task, which is the next sentence prediction, where we have two sentences and they can be following or they cannot be following. And then we ask the machine learning model, is this a follow-up sentence or not? And because of those two pre-trained tasks, the language model gets a really good understanding of the language itself, the context, and the relationship between the different words. And this is, nowadays we have a lot of derivative of BERT. This was the original BERT architecture, and in today's presentation, we want to focus on this architecture. So how does BERT work? So in 2018, there was a paper on the original transformer architecture, and the left side turned into BERT. With all the positional encodings, with our attention mechanisms and the feed-forward mechanisms. And then the left side turned into what we nowadays know as GPT-2 or GPT-3. How does it work in our context? So BERT, once it's pre-trained on a very gigantic corpus, and I think it is trained on like Wiki News or news articles and Wikipedia corpuses, then we can then fine-tune those pre-trained models. In this case, we can use it for named entity recognition, or we can use it for question answering scenarios, or better language understanding or domain-specific language understanding. BERT has like very specific tokens. So there's a CLS token and there's an SAP token, meaning the CLS token is basically what tells the transformer, here is where the sequence starts. And the SAP, our separation token, it tells the transformer model, this is where the sequence stops. And so we can put up to 512 tokens into that transformer, or you can less than that, or you can add less to the transformer. But this is basically the limitation due to the computation complexity, because everything gets parallelized in the computation inside of the attention mechanism. The output we get is basically two sets of vectors. One is a pooled vector, it's a single vector, it's a fixed dimension, and it represents the entire context of the input. And then we get the sequence vectors, where we get a context-specific vector for each token. And this is something really interesting for us to use. The ecosystem of BERT has spiraled out of control. This is already an older visualization, but We have now Ernies, and we have Distilberts and Alberts and all the different variations. Sesame Street is fully represented here, but they all have different purposes and different use cases. In our case, we stick to the original BERT architecture because we have a best understanding, and there was a lot of knowledge already in-house. So how does it work for our named entity recognition problem? So first of all, we would tokenize our strings. This is our banking transactions. This is what we would tokenize here. And then we would pass it through BERT. We would get our sequence outputs, our sequence vectors. And then we have a digits neural network, which is sort of classifying our sequence vectors into the categories which are interesting to us. So uninteresting or not interesting tokens are marked as O. And then the relevant tokens, for example, the dates, the entities, the phone numbers, the locations, and so on, they have their individual classifications, and that's something what we train the network for.
Okay, so now that Hannes has walked us through like how this theoretically works, and how do we bring a concept like that from an idea to production? So really, what we want is a straight shot. We want to experiment with the ideas a lot, prototype in our ML, in our Jupyter notebooks, and then release a production model. So this is a very simplified picture of what we want. So we do perform our prototyping all in Jupyter notebooks, and we also use like a smaller subset of the data available so that we can really focus on, rapidly prototyping and iterating quickly. So the production model, we use TensorFlow Extended to automate that pipeline so that we can do so in a repeatable and scalable way. However, in real life, this is all the steps that need to happen surrounding our prototype and production model. So in this more elaborate picture, we need to start from data annotation and end with the model deployment, which again feeds back into the data annotation. And we'll start by explaining each step, starting from data annotation. So for this named entity recognition problem, our task is to determine the relevant tokens, give them a specific label. So in the bottom example on the screen, you can see that we would like to identify Corner Bakery, California as the vendor here. And it's likely somebody ordered some pastries via Grubhub, which is a food delivery service, but it is the proxy here. And grubhub.com is a URL that occurred here, and New York is the location of this transaction. So there are a few data annotation tools available. So as you can see from the slide, and we just picked one for this purpose. So a next step is really to do fast iterations of prototypes in our Jupyter notebooks. And the goal here is really to build a model that shows that there is business values here and it is a good fit for the problem. Here we just train with limited amount of data so that we can prototype really quickly and iterate quickly. And so here, everything is done in a Jupyter notebook. It's not exactly production ready, but it does enable us to move very fast. Next step is once we have this really promising model that we would like to release to the world, how do we productionize it? And here is a lot of traditional data engineering processes like ETL, where we try to extract, transform, and load the data and standardize them with certain formats so we can repeat the training and model release process repeatedly. Here we would like to fine-tune our models and really start to focus on the integration pieces. We have to talk with our stakeholders and the data engineers to understand what kind of what is the service level agreement here. So what is an inference speed that is acceptable, and what is the output of the model's prediction response that can be consumed for the rest of the code. Next, Hannes is going to take you over the pipelines.
Yeah, once we're through the production or the prototype phase and we're heading towards the production model, we start building our machine learning pipelines. And here is the goal is we want to focus on the entire automation of our model update process. So let's say we get more data annotations, as Joe has mentioned that earlier, then this should trigger an update process where we get a new model version produced, which we then can evaluate in the following step. We have implemented those machine learning pipelines through TensorFlow Extended or TFX. And this gives us the great opportunity to perform model updates through Google Cloud's Vertex AI platform, in this case, Vertex Pipelines, which is a managed service to run those pipelines. In this case, we don't have to run Kubernetes clusters anymore. We don't have to install and maintain Kubeflow pipelines on our end. Once a model version is produced, then we have a variety of tools available to analyze them. TensorFlow Extended already comes with a TensorFlow model analysis tool, but also since we're on the TensorFlow side of the machine learning world, we can use the what if tool, and we can use Lime to analyze those language models or those text NLP models to get a deeper understanding of like how sensitive are those models to certain outliers or smaller changes. And then once the model is deemed to be production worthy, we focus on the deployment. Here at Digit, we have chosen TensorFlow Serving as our platform to deploy machine learning models. This gives us a really scalable opportunity because this fits nicely into our Kubernetes infrastructure. It also gives us the highest flexibility. Instead of using managed machine learning services, here we can fine tune each model or each deployment to really provide the lowest latency. So TensorFlow Serving, you can update or you can manipulate the way graph operations are being executed inside of the graph or in parallel of multiple models. And this gives us a great opportunity to really fine tune those settings on top. All the data which is passed through our machine learning models is fully encrypted because we can do the end-to-end encryption with TensorFlow Serving. Since we walked you through the process of how we go from an idea to like a production model, let's talk about what are the lessons learned. And one of the lessons we learned in the last couple of months was like the real machine learning problem often starts when the model is trained. Then we have to talk about how do we integrate it, how do we reduce the latency, how do we keep it up to date, and things like this. So there's a variety of challenges which we often forget when we talk about machine learning itself. So prototypes are really great, but machine learning models have to be integratable, meaning we could use a different model, like we could go to the state-of-the-art model, like the latest MUM model or T5 or BART or etc. But those models are much bigger and much more difficult to integrate. So using BERT or like a derivative of BERT, like Albert or DistilBERT, is a really good trade-off between state-of-the-art machine learning models and integratability and also complexity. Latency is really important. So there's always in production machine learning projects, there's a trade-off between latency and complexity or accuracy in this case. So there might be use cases where you want a really fast model for a quick prediction, but the prediction might have a lower accuracy, or in other cases you want a very high accuracy, but you're okay with a high latency. So what are the lessons learned? Optimizing for latency can really save money. We noticed this when we optimized the machine learning model and we took a few milliseconds out of those model inferences. Because of the huge volume of transactions we see on a daily basis, this can really save money and bring us closer to the real-time setup. Design thinking is really critical. We can have the perfect machine learning model if the design is not ready or the design is not really thought through. That could break our entire project. And we want to assist users. We don't want to alienate them. So meaning we don't want to replace them. We want to help all the users. And this is a really key design thinking here. At the same time, also from a broad point of view, investing into machine learning ops or feedback loops for around those machine learning models might look like an additional expense, but in the long run, this really pays off and it can be extremely helpful for your overall machine learning projects. Now, we want to focus a little bit more on the MLOps side. Key is here that we want to focus on reproducibility, repeatability, and scalability. The scalability is really important since Digits is growing rapidly, and so we see more and more transactions coming in every day. And the infrastructure we roll out today needs to be able to handle all the transactions of the future. So key here is that manual updates are very time consuming and error prone. If they happen on a manual basis, let's say models are being updated through notebooks, steps could be skipped, or like the evaluation could be inconsistent across different versions. So it makes it really hard to compare results end to end. We needed a framework where we can replicate our entire machine learning lifecycle with all the different phases. And we wanted a framework for our MLOps operations, which it doesn't lock us into a specific vendor. This is something where, SageMaker or maybe an Azure specific platform, it might be a downside over there. The lessons here were like TFX is really an interesting platform to think about because we can run it on GCP. We can also run it on any other cloud provider. There's no specific vendor lock. The TFX instructions are being compiled. They're getting converted into something which can be then executed on the AI Vertex platform. But they can also run with Airflow, Apache Beam, or Kubeflow pipelines. And it allows us to update our machine learning models, and then we can trigger them manually, and that would run through an entire CI/CD system for like machine learning, or we can trigger them automatically on like a cron job, things like this. And it allows us to replicate the entire machine learning lifecycle through this platform, TensorFlow Extended.
Cool. And the next area of learnings that we had was around code integration. And here, really, we're coming back to this customer first mindset, really. So where we really, to optimize for like the best integration, we have to think about customers first, optimize for engineering productivity, and how do we build in the feedback loops from our customers. So the challenges here is, yes, our model inference latency needs to satisfy our SLA, and the model predictions sometimes could be at odds with our existing models, right? The new model, regardless of how well it performs in our notebook, it could give a different answer than what the customers are seeing right now. And the evaluation of the ML model sometimes also need like a large amount of real data instead of like the subset of the data that we trained and saw in our Jupyter notebooks. And also just from a customer perspective, the net impact of our ML model has to be really positive overall. So it is people's financial data we're dealing with after all. Their trust in Digits in our product is the last thing that we want to put in jeopardy. So a few lessons we learned here is really, put customers first, use a design first and developer-centric approach. So we've learned that it really pays off to invest in the shared libraries that can codify your best practices. So we're talking about, so how do we parallelize model inference? We want to parameterize some of the things, changeable arguments from model to model. And so for instance, for this named entity recognition problem, we have a generalized library that's performing label sequencing. And for the other classification problems, we have a shared library just for classifications. And we want to pass through the model inputs into the output so that we can always retain the context of each prediction so that it can be integrated in the rest of the code in a very parallel way. The next thing we learned is really just a really fundamental principle in software engineering: separation of concerns. So as we mentioned, that this new ML model could be predicting something very different from all existing models. To really evaluate how it performs compared to the existing ones, we kind of need a lot of data, and here we want to separate the model predictions from how the predictions are being picked and ranked, so that we can have the maximum context and maximum options available when it comes time to pick them. The next lesson learned is a good versioning strategy also pays off, because regardless of how your ML model performs in your experiment, so the customers could be experiencing something very differently, and there might be a need for you to roll back easily. So we developed a versioning strategy where we always have a release and a pre-release model running in parallel, so that we can roll back to the previous one as needed with ease. So lastly, we really need to engage with design and product very early, front load the design in order to design for the false positive scenarios, and how to integrate it with customers' feedback loops. So this is very, very critical, because in real world, we're dealing with people's financial data, and Digits is always thinking about fostering trust with our customers. And the last thing that we want is this very cool ML model would erode the trust that we established with our customers.
So just to summarize our presentation here in a few bullet points, maintaining the entire machine learning value chain is really valuable. So from doing the annotations in-house through maintaining or setting up our own pipelines, through deploying the machine learning models on our infrastructure is valuable and helps us to fine-tune the models to the best latency or accuracy or whatever critical metric we want to use. The consideration of the complexity of the project is really important. I think this is often neglected when we talk about machine learning in research. Here we have a production problem where we could have gone with an even more recent machine learning model, but the complexity would have been tremendously higher. And then the investment into data annotation and machine learning engineering pays off. I think this is a critical statement here when we talk about how far do we want to go in terms of machine learning. I see companies sort of like running or training machine learning models in notebooks. And if you invest into automation and machine learning pipelines, there's a long-term investment effect from this. And there's a trade-off between what we discussed earlier, between the models and the higher complexity, improved models and higher complexity. Again, we could use a machine learning model like the latest MUM or T5 or BART, but the complexity would have increased tremendously. With that, thank you very much for taking the time to join us today. And if you're interested in joining Digits, let us know. You find open positions currently on our website. There's also a machine learning engineering position. So let us know. Send us a message and ping us via Twitter or via the website. Thank you.
Thank you so much to both of you. It was such an interesting presentation. So I don't see any question in the chat, but if you don't mind, I'm gonna start with my question because I have a couple of questions. So maybe people will feel more confident and start to write their own.
Sounds great, Nadia.
Okay, so I have previous experience working with transaction and also with NER, and sometimes the entity that you want to recognize, they come up like without space. So they are kind of attached one to the other one. And I feel like that is the major pain point when you work with entity recognition problem. How do you usually tackle this problem?
That is a very common problem in the field of financial transactions. Words can be scrambled, shortened, white spaces can be removed or white spaces can be added. There's a couple internal tricks we have applied, something we can't really share, how we tackle some of those details, but one of the things which everybody else can apply is with modern transformers, they either use word piece or sentence piece tokenization. In those cases, we're not splitting on white spaces anymore. We're splitting on like most frequent tokens, and that could be an approach of getting around it. There's a couple things you can do to improve the accuracy even further, but as a first measure, using sentence piece or word piece tokenization would be a way to go.
Okay, thank you so much. Do we have any other question? Come on, people, don't be shy. We have two really good source of knowledge regarding NLP, so I think it might worth to ask some question. We have the first question. So, okay, so are there specific challenges you face when deploying web apps powered by ML?
Yeah, so there are a lot of challenges, as we mentioned. I think we kind of stayed at the high level at this talk. So Digits is, running on the website. It is a website. So, people's experience with web apps is like it has to be loading really fast. So we don't, for instance, we don't do like on the fly inference, like as they're loading the page. Everything is kind of pre-computed but refreshed regularly, so we can't really keep up to our real-time promise. So the specific challenge here is, I think, on one hand, it's like the generic, like web engineering challenges is we do have an SLA here that we need to honor. Like, how do you speed up the loading of your website, your requests? So I think it's like generally applies everywhere, as in other fields as well. So specifically with ML, I think it goes back to that customer first approach. Is like when we pre-computed a view with a combination of ML predicted results and other heuristics predicted results, and even the customers, the human inputs from their own accountants. So how do we like rank the priority of each to really, tell a good story here and to like establish the trust of our customers in Digits? So that is, I think, like sounds weird to hear it, but it's again, it's a customer experience. Yeah, the key is customer experience.
Thank you so much, Joe. We have another question. So how to identify noise versus signal in documents?
Oh, so, Hannes, you're muted. Yeah.
Yeah, you're mute.
In terms of, sorry, maybe the question, maybe the question can be clarified.
I don't know if I understand correctly the question, but I think it's like identify real entity versus noise. So words that instead are not entity. Did I got it right? That's your question, Vikas? Let us know.
So for this particular named entity recognition problem, it's really critical that the data is very clean and that there's a very careful annotation happening. It is not like automatically generated or like a same as supervised problem where there is a lot of noise, or there could be a lot of noise, and then other technologies would be used like noise reduction mechanisms and things like this to suppress like noisy labels or things like that. So here in this particular case, we paid attention that the annotations are very clean and very well moderated.
Okay, thank you. So, yeah, I think the question was kind of in that way. There is an example but it doesn't really apply to transactions. So I think Vikas, feel free to ask a follow-up question if you need it. Okay. We do have another question. So you use BERT for your current application. You've also mentioned other flavors of BERT. BERT flavors and flavors of GPT. Even though BERT has considerably more hair than myself, okay, do you have any comments on Ernie and other BERT flavor and GPT as you might use the mean of your organization? I don't know.
I think we need to distinguish in two categories. So first of all, there's like the BERT-like transformers. This is like a transformer architecture, which is often used for classification tasks, for sequence classifications, for like groups of like mathematical operations where we can then use those representations of our vectors or of our tokens for some classification task or labeling or etc. GPT 2.3 are generative models. So that's something the BERT architectures are not being used to generate text in general cases. Then within the BERT family, we have like nowadays we have Alberts, we have the DistillBERTs, we have various other BioBERTs, and there's even a COVID version of BERT. Those are either domain-specific models, which are trained on domain-specific corpuses, or they have been reduced in terms of their size, the memory footprint, their computational complexity. As an example, Albert is one of the distillation models, or like that model is trained through teacher-student forcing, where we take a BERT model and then we teach a smaller model with fewer weights and fewer connections what the correct prediction would be. And it's basically teaching, a student is teaching from a teacher, in this case, BERT. And so there's a variety of other types and tricks. Some models are generated through pruning, or some of them have been quantized, meaning that float 32 weights have been reduced to integer 8, or float 16 variable representations, which reduces the memory footprint even further.
Thank you so much, Hannes. We now have another question. It's more on your company. So people are curious to understand how the team is structured. Do you have a dedicated data scientist, ML engineer, or for other aspects of the life cycle, like the DevOps or the developers?
Yeah, Hannes, you want to take this one?
I can give it a start, and then you can chip in. We have a data team. This is a very focused team on all data tasks. And then within the team, we have data engineers and machine learning engineers. But these days, I think the roles are sort of like mixing and matching. Joe's traditionally a data engineer, but she's handling a lot of machine learning tasks. So we don't have that structure of like larger companies like the Spotifys, the Airbnbs, where you have like dedicated machine learning ML ops people, or like you have machine learning engineers, and it's a distinction between data scientists and machine learning engineers. We're too small and a too focused company to have that division. We're just focusing on the data group, and then we're handling all tasks from there.
Yeah, the roles here are pretty dynamic. I would say I really enjoy this structure where, to kick off a project, we may start with a chat just with product stakeholders and designers, just trying to understand what is the customer ask here, like how do we deliver the optimal experience, UX for the customer, and like the things that we touched on in the slides, how do we think about like the extreme cases, like the false positive scenarios, how do we design for the user feedback loops so that, it's already thought of ahead of time, instead of like your model is just getting inserted in this very blunt way that users may not understand how to use it or what you're suggesting, even though just in pure mathematical numbers, they look stunning.
Thank you so much, Joe. Okay, so this one was our last question. I don't see any other coming in. So thank you so much, guys. It was really an interesting presentation. I really hope you will share your slide, because there is a lot of good content there. So thank you so much again. And yeah, thank you, everyone.
Thank you, Nadia. Thank you, everyone. It was great to to be here and present for you. Thank you.
Thank you so much. Enjoy the rest of the conference, everyone.
Bye.
Bye.